So this lecture we're going to put to work the mathematical techniques that we've developed for solving a special class of second-order ODEs, so second-order homogeneous linear ODEs with constant coefficients. And we're going to put those techniques to work in the context of a physical system of the mass on a spring. And our mass on a spring we can add a drag force to it as well. So we'll have a more complicated simple harmonic oscillator, what we call a damped simple harmonic oscillator. So to organize our thinking, I want to talk a little bit about all the different cases that you can have for the solutions of the characteristic equation. You can have two real roots or two real solutions, two complex solutions, or you could have one repeated root of the characteristic equation. And those three cases will have physical interpretations as well with a mass on the spring. We call them overdamped, underdamped, and critically damped. So that's the kind of main take-home that I want to get through in this lecture, is recognizing that those three cases are related to three physical cases of the mass, of what's going on with the mass on the spring. Just to remind you where we've been, we've already talked about the case where the characteristic equation has two real roots. So that's where we're guessing y is equal to e to the rt, and we got two real numbers, r1 and r2, were the solutions of my characteristic equation. And so we got our general solution was e to the r1 times t plus b e to the r2 times t. So this is sum of exponentials. So it's exponentials. Just to be clear, these are real numbers. And they're smooth. There's no oscillations here. It's smooth. For example, if you were to visualize this, this is just a particular example, but the idea is kind of the same. If r1 is equal to 1 and r2 is equal to minus 1, you have an equation, a solution which maybe looks like this. Y is equal to e to the t plus e to the minus t. If you graph that, it looks like this. It's a smooth function. There's no wiggles, there's no oscillations. Okay? So if the roots of the characteristic equation are real, there's no oscillation. So that's important observation. We're going to be concerned about when does the solution oscillate and when does it not oscillate. So if the roots of the characteristic equation are real, there's no oscillations. It's a smooth function. Okay, now let's talk about what if the roots of the characteristic equation are imaginary, and then later on we'll talk about what if they're complex. We'll talk about what the solutions look like in that case. Let's go back to physics and talk about the simple harmonic oscillator again. So we have the mass on the spring, which we've seen many times, and we've got the spring force causing the acceleration, gives us this famous ODE for the simple harmonic oscillator. Earlier in the course we had worked out the general solution of this equation, and that's what I'm writing here. So this is something we arrived at mostly by guessing, by thinking what kind of function do I know where I take two derivatives of it and I get the thing back again multiplied by a negative constant. And we decided it was a cosine or a sine, and we played with it a little bit and able to get this equation. Now that we know how to do complex numbers, we can apply the techniques for solving this kind of ODE. This is a second order constant coefficient linear homogeneous ODE. So we can apply the usual techniques and let's see what happens. So alternatively, you could do the standard technique, guess x is equal to e to the rt, and you plug it into the ODE, and what you get for your characteristic equation is minus r squared, r plus r squared, plus omega 0 squared is equal to 0, which gives me r is equal to plus or minus I omega 0. And that gives us our, so I have complex solutions to my characteristic equation, or imaginary solutions. And so my equation would be x of t is some constant e to the I omega 0 t. This is my general solution, plus some other constant e to the minus I omega 0 t. So now you look at this equation and you compare it with the one above, and they look different. One has e to the I omega t, the other one has cosine and sine. But you know that those are related to each other. So to see the correspondence, let's first try to remove a and b in favor of xi and vi. So let's apply the initial conditions. IC is initial conditions. So we'll take xi is going to be plugging in t equals to 0, I get a plus b. And then maybe I should take the derivative. So v of t is the derivative of x. So that's going to be a times I omega 0 e to the I omega 0 t minus b times I omega 0 e to the minus I omega 0 t. And then I can plug in t equals to 0 into that equation. I get vi is equal to a times I omega minus b times I omega 0. Okay, that's a system of equations you can solve for a and b. And I won't do too much of the algebra, so let me just show you what the solution is. So there it is. And so now I can plug that back in, and I get x of t is equal to a, which is, so I'm going to have a 1/2 out in front of everything, xi minus I vi over omega 0, e to the I omega t, omega 0 t, plus xi plus I vi over omega 0, e to the minus I omega 0 t. So there's a second solution written in terms of complex exponentials. Still looks different than above. So the claim is that those are actually the same. The equations that I just wrote in the red boxes are the same. And I'm going to leave that as an exercise for you. So exercise. Use Euler's formula to show the two equations in boxes, red boxes, are the same. So the upshot is we got this solution by guessing sines and cosines, and then we got this solution by using the techniques of second order ODEs that we've been working on. And the claim is that both of those work. So even though they look different at first sight, they're actually the same solution, just written a little bit differently. So either way is an acceptable way of solving a second order ODE. This brings us to an important point. So we understand that this mass is going to oscillate back and forth here on the spring, oscillating back and forth, left and right. And we know we can describe that in terms of sines and cosines, but we can also describe it in terms of complex exponentials. So what we've learned is the following thing. Is that if the characteristic solution, the characteristic equation to the ODE has imaginary solutions and that was the case that we had here, right? Plus or minus I omega 0, those are two imaginary solutions to that characteristic equation. The solution is oscillatory, meaning it can be written in terms of sines and cosines, or it's something that oscillates back and forth and back and forth. So if you have an imaginary solution to your characteristic equation, you have an oscillating function. And this oscillating function in this case has a physical interpretation of the mass going back and forth on the spring. Okay, what if they're not perfectly imaginary, but what if they're complex? What if they have a real part and an imaginary part? So we'll do an example of that starting next. As a warm-up to looking at the harmonic oscillator, let's do this simple math problem here. So solve this ODE with these boundary conditions that are given. And this is going to be an example where the roots of the characteristic equation are complex, not real. They have a real imaginary part and an imaginary part. So I'm going to do this one a little bit quick. I'll kind of do a lot of steps offline so that I won't take a lot of time with the video. So the first step, of course, is to guess our usual y is equal to e to the RT and plug in. And that gives us our characteristic equation. So there's the equation that you get. And then, whoops, so it'd be a plus. And then let's solve that equation very quickly. So that's what happens when you solve the quadratic equation. You can see there's two roots here, R1 and R2, and they're complex conjugates of each other, minus 1 plus 3i, minus 1 minus 3i. So let's write our general solution now. And there's the general solution. And we can take the derivative just like that. Okay, and as usual, applying now the initial conditions here gives us two equations so we can solve for a and b. So those two equations can be found as follows. Okay, and I'm going to do some algebra now, so I need to solve these for a and b. And here's the result when you do the algebra to solve for those two, for a and b. So it gives me my my solution for y. And let's put it all together and write an equation for y. So y of t, my solution which meets the boundary conditions is, there's a 1/2 in both terms, and then I've got 1 minus I over 3 times e to the minus 1 plus 3i times t, and then I have plus 1 plus I over 3 e to the minus 1 plus 3i over t. Sorry, 3i times t. Okay. So there's my solution with the boundary conditions. Okay, so just a quick example illustrating those techniques. Now, let's think about what is this function actually doing as a function of time. So how do I visualize this solution which we've just found? It's a little bit hard to visualize with the complex exponentials like that, and then the coefficients are complex. So I'm going to do a couple things. First thing I'm going to do is that both of the terms have an e to the minus t. So there's an e to the minus t here and an e to the minus t here. So I'm going to pull those out. And then I'm going to group together the real parts and the imaginary parts. So let's pull it out. So I'm just rewriting this in a way that's going to be more obvious what's going on. So e to the minus t can come outside because I have that in every term. And then I've got 1 minus I over 3 e to the 3it. And then I've got plus 1 plus I over 3 e to the minus 3it. And then what I'm going to do is put the real parts together and the imaginary parts together. So here's the real parts, e to the 3it plus e to the minus 3it. So that came from this term here and this term. And then we're going to put together everything that has an I in it. So I, and, well, let's put the I over 3 because the only imaginary parts have I over 3. And then I've got here e to the minus 3it minus e to the 3it. Let me do one more step where I'm just going to flip the sign in the last term there. Like that. Okay, why did I bother writing it like that? Because I know that if I see e to the x plus e to the minus x with an I, so e to the ix plus e to the minus ix, this is 2 times the cosine of whatever's in the exponent, 3t, without the I. And then here, e to the 3it minus 3 to the minus e to the minus 3it, this is 2I times the sine of 3t. If you can't see that, you go back to the lecture on Euler's formula. So this is a simple application of Euler's formula. E to the I theta is cos theta plus I sine theta. And then everything kind of simplifies. So what I have now is I've got a 2 everywhere. So these 2's cancel with this 2, and I get e to the minus t cosine of 3t. And then I've got minus I times I, which makes plus 1. So I get plus 1/3 times sine of 3t. So this is what my function is doing. There's 2 pieces to it. There's an oscillatory piece. So this is the oscillation. Cosines and sines. It's a periodic function oscillating in time. And then there's this thing sitting out front of here, right? This is like a amplitude which depends on time. Okay, so a couple of important things to note here. So important observation, I use a different color. If the roots of the characteristic equation are complex, which is what we have in this example, I do have an oscillatory solution. So it's a solution which is oscillating in time, periodically, with sines and cosines. However, there is this extra complication of this thing out front. So for this regular simple harmonic oscillator, we didn't have that. And now when I have the complex roots of the characteristic equation, I do end up with an amplitude which changes with time. Here's a simple concept quiz on the thing we've just learned. So we've seen that when your characteristic equation has complex roots, you often see the following combination show up. E to some real number times t times a cosine or a sine, or some combination of cosines and sines. So you have an e to a real number times t, so an exponential function, times a cosine or a sine. And just to build intuition, what does that look like if you graph it? So if you graph e to the minus t times cosine 3t, which of these four graphs is the thing that you will see? So make sure you can understand this, what this function looks like before going forward.